Module C, Parallel Gatekeeping Strategies. In Module B, we introduced key ideas and concepts that play important roles in clinical trials with complex, hierarchically arranged objectives. These objectives, or equivalently the corresponding null hypothesis of no effect, are typically grouped, as we said, into families, and the families are examined sequentially. Each family in this sequence serves as a gatekeeper for the next family, and there are three types of gatekeepers: serial gatekeepers, parallel gatekeepers, and general gatekeepers. With serial gatekeepers, testing strategies are defined in a trivial fashion. Each hypothesis within a serial gatekeeper is simply tested at the full alpha, for example, one-sided alpha of 0.025, and this approach guarantees that the overall type 1 error rate will be controlled at this alpha level. In this module, I will introduce general approaches to constructing gatekeeping procedures for trials with parallel gatekeepers, and in Module D, we will extend this setup to go over multi-family problems with general gatekeepers. So first, in section C1, we will briefly introduce basic nonparametric, which means Bonferroni-based, nonparametric parallel gatekeeping procedures that are essentially derived from chain procedures, also known as graphical procedures, in a parallel gatekeeping setting. This will not take too much time because we're mostly interested in more powerful gatekeeping procedures. And section C2 will introduce semiparametric parallel gatekeeping procedures, for example, Hogberg-based procedures that lead to more efficient multiplicity adjustments compared to basic Bonferroni-based gatekeeping strategies. Section C1, nonparametric parallel gatekeeping procedures. In part 1, we discussed the key principles that drive the selection of appropriate multiple testing procedures in confirmatory phase 3 trials. The first principle tells us that it is crucial to ensure that an appropriate procedure is fully aligned with the trial's objectives, which means, in plain English, that it takes into account the relevant logical relationships among the objectives, and that translates into logical restrictions among the null hypotheses of no effect. This means that the multiple testing procedure does not impose unnecessary restrictions, which may happen, for example, when a trial's sponsor may force certain hypotheses to be tested in a strict hierarchical manner, but in reality, these hypotheses do not depend on each other hierarchically. So this will be an example of unnecessary or even unnatural restrictions. And the second principle states that an appropriate procedure needs to efficiently utilize all available distributional information, which means that the information on the joint distribution of the hypothesis test statistics must be incorporated into the decision rules for the individual hypothesis tests. The key point to remember here is that the more information on the joint distribution of the test statistics of a procedure utilizes, then the more efficient the multiplicity adjustment will be, which means that the higher the probability to reject each individual null hypothesis. In this section, we will focus on logical restrictions that are consistent with parallel gatekeeping conditions. As far as distributional assumptions are concerned, we will discuss procedures that are derived from nonparametric tests, such as the Bonferroni or the Holm test. And we know that this is not the most efficient approach to multiplicity correction, because nonparametric procedures are generally less powerful than, say, semiparametric procedures. But this class of simple gatekeeping procedures will help us set the stage for a discussion of semiparametric strategies in section C2. Now, after this long introduction, let's take a look at example 2. This slide and the next slide in this module actually come directly from module B, where we introduced parallel gatekeepers. And The idea of parallel gatekeepers was introduced using example 2, which is based on the type 2 diabetes trial, in which 3 dose placebo or regimen placebo comparisons were grouped as shown on this slide. There were 2 hypotheses, H1 and H2, included in the primary family, and a single hypothesis, H3, is included in the secondary family. This diagram shows us the relationships among the hypotheses in this multifamily problem, and it is helpful to note that the sponsor could have considered a serial gatekeeping restriction in this type 2 diabetes trial, in the sense that the primary family could have been a serial gatekeeper. This will be a fairly restrictive approach because with a serial gatekeeper, the secondary hypothesis H3 can be examined only if both primary hypotheses are rejected. It is more meaningful to consider a parallel gatekeeping strategy in this particular example, and this is what is shown on the slide. As you can see here, that there are 2 arrows that represent decision-making paths that connect H1 to H3 and H2 to H3 as well. And that means that family 1 serves as a parallel gatekeeper for family 2. Formally, going back to the definition of a parallel gatekeeper, with a parallel gatekeeper, at least one null hypothesis must be rejected in the primary family to claim that the trial has met its primary objective and proceed to testing the hypothesis in the secondary family. In this case, there's only one hypothesis, of course, in the secondary family. And this strategy obviously enables the sponsor to build a more flexible testing algorithm, and it will potentially enable the sponsor to include the secondary comparison in the product label if at least one primary comparison is significant. Parallel gatekeeping strategies rely on what could be called a trickle-down principle, which can be introduced using this diagram. Here we assume again a simple 2-family setup. There are k hypotheses in the primary family, which is family 1, and without loss of generality, we can assume that there are k hypotheses in the secondary family, which is family 2. We can think about the individual boxes included in family 1 as clouds up in the sky, and if at least one of those hypotheses is rejected, the amount of water within that cloud can rain down or trickle down to the secondary family. And roughly speaking, even though the first procedure 1 in the primary family will always be applied at the full alpha level, as explained at the bottom of the slide, the significance level that will be applied in the secondary family with procedure 2 will be a data-driven random quantity. That alpha 2, which is the local significance level utilized within the secondary family, will depend directly on the number of null hypotheses rejected in the primary family. The trickle-down principle can be illustrated using a general example with a 2-family multiplicity problem by constructing a simple chain-based gatekeeping procedure. This gatekeeping procedure would test the null hypothesis included in the primary family, family 1, using the Bonferroni test, and in family 2, any appropriate multiple testing procedure that provides local alpha control could be applied. Examples would include, for example, the Holm procedure. In the context of example 2, this chain-based parallel gatekeeping procedure simplifies to the following diagram. There are 2 hypotheses within the primary family, and they will be tested using the Bonferroni procedure. If at least one of those primary hypotheses is rejected, we're going to step down to the secondary family, and since there is only one hypothesis within that family, it will be tested using an appropriate alpha level univariate test. To set up a parallel gatekeeping strategy for the simple multiplicity problem in example 2, we will need to refresh our memory and go back to this section in part 1 of this online training course where we talked about the structure of chain or graphical procedures. The class of graphical procedures, as I emphasized in part 1, supports very flexible testing strategies, and this is due to the fact that chain testing algorithms are built using the following two rules. They're known as the alpha allocation rule and the alpha propagation rule. First, we're going to take a look at the alpha allocation rule for the chain-based parallel gatekeeping procedure for example 2. As we said, what we need to do at this point is to predefine hypothesis weights that reflect the clinical importance of the individual null hypothesis. And in this case, it is important to make sure that non-negative weights will be assigned to the hypothesis within the primary family, and the zero weight will be assigned to the secondary hypothesis H3. In this diagram, I have assumed that the hypothesis H1 and H2 are equally important. This may not generally be the case, and therefore the weights W1 and W2 may not necessarily be the same. Again, for simplicity, let's assume that we're dealing with an equal alpha splitting strategy. What's important to emphasize here, once again, that W3, the initial weight of the hypothesis H3, should be set to 0. This is how we ensure that this is a secondary hypothesis that can be tested only if at least one primary null hypothesis is rejected. When we move on to the definition of an alpha propagation rule for this chain-based gatekeeping procedure, we need to recognize, as I emphasized a couple of minutes ago, that not all of the transition parameters will be meaningful in the context of this particular clinical trial example. In fact, we're only interested in transferring alpha from H1 to H3, which means that the parameter G13 will be defined. And also, we're interested in transferring potentially alpha from H2 to H3, which means that the parameter G23 will be defined. And in this case, both of those parameters will be set to 1. What does that mean? That simply means that whenever we reject the hypothesis H1, all of the significance level that was used in that test will be transferred directly to H3, and the same rule will apply to the hypothesis H2, and for the same reason the transition parameter G23 will be set to 1. Formally, when we talk about alpha allocation and alpha propagation rules for general chain procedures, they are defined using the vector of hypothesis weights and a matrix of transition parameters. This formulation of chain procedures will come in handy when we will talk about software implementation of chain-based parallel gatekeeping procedures. In this particular clinical trial example, as we said on slide 12, we assume that the primary hypotheses are equally weighted, equally important, and therefore the initial weights, which are the first two elements of the vector W, are 0.5 and 0.5. Once again, and that's a very important point, the initial hypothesis weight for H3 is set to 0. That is the only way for us to make sure that this hypothesis will not be testable unless at least one primary hypothesis is rejected. Now, moving down to the matrix of transition parameters, each element within this matrix specifies the fraction of alpha that will be transferred after a certain hypothesis is rejected to the remaining non-rejected hypothesis. In example 2, when we look at the first row of this matrix, we see that the first two elements are equal to 0. The last element is equal to 1. That means that if the first hypothesis, which is H1, is rejected, all of its weight, all of its significance level will be transferred to the third hypothesis, which is H3. And using exactly the same rule, we see that when the second hypothesis, which is H2, is rejected, then all of its weight will be carried over to the third hypothesis in this problem. Once again, this would be H3. I think it will be quite helpful to go over the specifics of the alpha propagation rules in this clinical trial example. And the best way to summarize alpha propagation rules in more complex problems of this kind is by using a diagram that shows the weights that will be transferred to the hypothesis H3 depending on possible outcomes in the primary family. On this slide, we're going to assume the case when both null hypotheses in the primary family are accepted. That's why the two orange boxes here are grayed out, and I put the letter A within each box. A here stands for accepted. In this case, we're dealing with a situation when no hypotheses are rejected in family 1. As a result, no alpha propagation is going to occur, and the weight of H3 will be set to 1, which means that this hypothesis is accepted without testing. This approach is fully aligned with the predefined parallel gatekeeping restrictions that state that the primary family can be passed and the secondary tests will be carried out only if there is at least one rejection in the primary family, which is obviously not the case. Another set of outcomes is graphically summarized on slide 16. In this case, we see that only one hypothesis, specifically H1, is rejected in the primary family. That's why the box that corresponds to the hypothesis H1 is still orange, but H2 is not rejected. That box is grayed out. Because of the predefined alpha propagation rule, we can take the weight, or in other words, the fraction of the overall alpha that was used in the test of the hypothesis H1, and we can propagate it or carry it over to the hypothesis H3. As a result, the initial weight of the hypothesis will be updated. It used to be 0 before we started this testing process, and now it is updated to 0.5, and as a result, this hypothesis can be potentially rejected if its p-value is significant at the alpha over 2 level. The most optimistic set of outcomes is presented on slide 17. This is the set of outcomes that corresponds to the rejection of both primary hypotheses. That's why I've replaced the hypothesis labels by R, rejected, H1 is rejected, and H2 is also rejected. With this most optimistic set of outcomes, we see that the weight of the hypothesis H1 is now set to 1. This weight was updated to reflect the fact that H1 was rejected, and therefore half of the alpha was carried over to the hypothesis H3. And in addition to that, we should not forget that H2 was also rejected, which implies that the other half of the alpha was carried over to the hypothesis H3. The updated weight is now 1, and that implies that if both hypotheses are rejected in family 1, then the secondary hypothesis H3 will be tested at the full alpha level. Now we are ready for a quick summary, and to provide a quick summary, in section C1 we went over the underlying rules that are used in simple parallel gatekeeping procedures that rely on the Holm or Bond-Fournier tests. These gatekeeping procedures are equivalent to the chain or graphical procedures that we discussed in part 1. They are easy to construct and they're easy to implement in real-life clinical trials, but a key property of chain procedures is that they are memoryless procedures. What do we mean by that? That means that a chain procedure handles only one hypothesis at a time, and if this hypothesis is rejected, this rejection triggers a series of actions for the remaining non-rejected hypotheses. For example, as we have discussed, the hypothesis weights are updated, transition parameters can be updated as well, but all of those decisions made prior to this rejection will be erased from the procedure's memory. Those decisions cannot be taken into account when future decision rules are formulated, and practically speaking, this means that chain procedures cannot be used in multifamily multiplicity problems with complex logical relationships among the null hypotheses. For example, chain procedures cannot be used in clinical trials with general gatekeepers. I need to mention that advanced chain procedures, or as they're known, chain procedures based on entangled graphs, could be potentially set up for problems with complex types of logical relationships, but as I will show in Module D, we now know how to build more powerful semiparametric gatekeeping procedures in these more challenging situations, and for this reason, we're not going to go over advanced chain procedures in this online course. Semiparametric gatekeeping procedures from Module D will do a better job and they will support more efficient adjustments. Section C2, semiparametric parallel gatekeeping procedures. I explained in section C1 that chain-based parallel gatekeeping procedures are based on the following simple alpha propagation rule. If we assume a more general setup, not necessarily thinking about example 2, let's assume that there are two hypotheses included in the primary family or family 1, and those hypotheses will be tested using the basic Bonferroni test, and there's a larger set of primary hypotheses. Let's assume that those will be tested using the Holm procedure. The underlying alpha propagation rule is given at the bottom of the slide. If H1 is rejected, then half of the alpha, assuming that the hypotheses are equally weighted, half of the alpha will be transferred to the second family, and in addition, if H2 is also rejected, then its predefined fraction of the alpha, alpha over 2 for example, will be transferred to family 2. That's a simple and attractive alpha propagation rule, but now I would like to reiterate an important point that I made earlier in this module. Basic testing strategies that rely on the Bonferroni procedure can be used in any trial, and on the surface there is nothing wrong with them. After all, they control the overall type 1 error rate, but we ought to remember that these strategies will be inefficient and they will lead to power loss because they do not account for the available distributional information. For example, the hypothesis test statistics may be strongly positively correlated, but this information will be ignored by Bonferroni-based parallel gatekeeping procedures. In the context of example 2, if we assume a balanced design was used, which means that the correlation between the test statistics in the primary family is equal to 0.5, a chain-based gatekeeping procedure is not going to be able to utilize information, even though this is not a trivial correlation. More efficient testing strategies can be set up here based on semi-parametric procedures, for example, Hogberg-based or Hamel-based procedures, and in addition, parametric multiple testing procedures could be potentially considered, for example, Dunning-based procedures. A key feature of these semi-parametric or fully parametric procedures is that they will exploit positive correlations among the tests in a multiplicity problem. For example, as we said a second ago, they will exploit the positive correlations between the test statistics for H1 and H2, and this will result in a power gain over basic Bonferroni-based procedures. As an alternative to the nonparametric chain-based procedure that we defined on slide 20, we could consider the following semiparametric gatekeeping procedure, which is derived from the Hogberg test. This testing strategy provides an improvement over the nonparametric procedure because instead of using the Bonferroni test in the first family, this strategy applies a more powerful Hogberg procedure. And when we look at the secondary family, we see that the Holm procedure is replaced by the Hogberg procedure, which is known to be uniformly more powerful. To be able to construct a parallel gatekeeping procedure based on those two components, the Hogberg test in the primary family and the Hogberg test in the secondary family, we need to answer the following very important question. What is the alpha propagation rule that needs to be used in this case to ensure that the overall type 1 error rate will be controlled? To answer the question we asked, I'm going to compare the component procedures used in the nonparametric and semiparametric parallel gatekeeping procedures. Well, assume first that we have a generous component procedure, for example, Bonferroni, used in the primary family as on slide 20. In this case, we said that a fraction of the overall alpha can be transferred to the secondary family even if some null hypotheses are accepted in the primary family. The reason it is possible to transfer some alpha in this case is that the Bonferroni is a generous procedure. It is quite inefficient and it easily gives away some alpha. By contrast, if we consider a greedy component procedure, for example, the Hogberg procedure in the primary family as defined on slide 21. What do I mean by greedy? I mean a very efficient and powerful multiple testing procedure that tries to spend as much alpha as it can. This is how we generally achieve efficiency, by utilizing all available resources. In this case, we have an efficient multiple testing procedure such as the Hogberg, and it tries to use up all available alpha. So going back to the question we asked on slide 21, if a greedy component procedure such as the Hogberg is selected in the primary family, we make a heartbreaking discovery that all alpha will be used up and nothing can be transferred to the secondary family if some null hypotheses are accepted in the primary family. For example, if exactly one hypothesis is rejected in the primary family, nothing can be carried over to the secondary family. Why did I say heartbreaking? The reason is that the fact that we cannot transfer any alpha to the secondary family if only one hypothesis is rejected in the primary immediately tells us that we cannot build a parallel gatekeeping procedure that utilizes the Hogberg in the primary family. We wanted to set up a more powerful parallel gatekeeping procedure compared to the basic chain-based procedure, but it seems like we may not be able to accomplish this goal. But never fear, the great news here is that we can construct more powerful Hogberg-based or perhaps Hommel-based parallel gatekeeping procedure, and I will tell you more about this on the next slide. To enable more powerful semiparametric parallel gatekeeping procedures, we need to go back and make use of a general methodology for building multi-stage parallel gatekeeping procedures that was introduced in our paper in 2008. The key features of this approach include the fact that it is based on a simple algorithm which streamlines implementation of those procedures and communication of results to non-statisticians, and the procedure is constructed from building blocks known as component procedures that it as a result has a very flexible structure. To introduce this general method for constructing multi-stage parallel gatekeeping procedures that could have powerful semiparametric components, I'm going to need to introduce some notation. That's what I'm going to do on this slide. We're going to assume once again a straightforward two-family multiplicity problem. We will assume that there are k null hypotheses in the first family. They're denoted by h1 through hk. We're going to introduce the index set. This is the set of indices of the hypotheses in the primary family. This index set is going to be denoted by n1, and it's simply equal to the set which includes all of the indices 1 through k. We will assume that a separable or a generous procedure that provides local error rate control is applied within the primary family. We will call it procedure 1. I'm going to explain in a few minutes what I mean by a separable procedure. Now, continuing to family 2, we here also have a set of null hypotheses, a corresponding set of indices within the secondary family. And here, since we are at the end of the testing sequence, we don't have to worry about restricting our attention to separable or generous procedures. Here we can apply any procedure that provides local family-wise error rate control. So here there would be nothing wrong with using the Hogberg or even Hummel procedure. An important result that we proved in our paper in 2008 is that a general family of powerful multi-stage parallel gatekeeping procedures can be defined using the following approach. It results on the following alpha propagation rule. Within family 1, which is the family of primary hypotheses, we're going to apply a separable procedure at the local level defined by alpha 1, and that local level is set to alpha, which means that we're going to try to maximize power of the primary testing strategy. After we have applied the procedure, we can determine how many in which specific hypotheses were rejected. We're going to define the index set of the null hypotheses that were accepted in the primary family. That index set is going to be denoted by A1, and of course is going to be a subset of the index set corresponding to the entire primary family. If at least one hypothesis is rejected in the primary family due to the predefined parallel gatekeeping conditions, we can proceed to testing the hypothesis in the secondary family. We're going to apply the predefined procedure, which is denoted by procedure 2, and it will be applied at a potentially reduced local significance level, denoted by alpha 2. The formula for computing alpha 2 is shown on the slide, and this formula essentially defines that alpha propagation rule that we were looking for. According to this formula, the local significance level to be applied within the secondary family, alpha 2, is equal to alpha 1 minus a certain quantity. This quantity is a penalty for not being able to reject some of the hypotheses in the primary family. This quantity is known as the error rate function, and it depends on A1, which is once again is the index set of null hypotheses that were accepted in family 1. Roughly speaking, the more null hypotheses we accept in the primary family, the higher this penalty is going to be, and as a result, the lower the significance level alpha 2 is going to be. That is the price that we'll have to pay to be able to control the overall alpha. But the great news now, with this very flexible setup, we were able to show that the global family-wise error rate, or the overall type 1 error rate, in this two-family multiplicity problem will be controlled at the pre-specified level alpha. We're now ready to define the error rate function of an arbitrary multiple testing procedure, and I must admit that this material presented on the slide may be quite dry and too mathematical. To give a formal definition of the error rate function of an arbitrary multiple testing procedure, we need to select a subset of the null hypotheses in the multiplicity problem at hand. We will assume that all those hypotheses are true. The error rate function E will be equal, as you can see in the formula at the bottom of the slide, it will be equal to the error rate for the subset of null hypotheses, which means it will be the probability of rejecting at least one null hypothesis in the subset. Now, what does this mean? What is very helpful for us to remember is that in the world of closed testing procedures, and here we're dealing with closed testing procedures, true hypotheses can be treated as if they have been accepted. What this definition of an error rate function tells us is that the error rate function determines how much alpha is lost if all hypotheses in the index set I are accepted by the procedure we are considering. If we look at error rate functions from this angle, it will be quite easy to understand there are key properties that will be listed on the next slide. The two most important properties of any error rate function are defined at the top of the slide. First, if the index set or the argument to this function is empty, the error rate function e is simply equal to 0. Why is that? I explained on the previous slide that the error rate function tells us how much alpha is lost if all hypotheses in the index set are accepted. In this case, if the index set is empty, that means that the error rate function is 0, and thus there is no alpha lost in the primary family. All of the alpha can be transferred to the secondary family. The second property states that if the index set I is equal to n1, that is, and this is the index set that contains all hypotheses from the primary family, then the error rate function e is equal to alpha. In plain English, this means that all of the alpha will be lost if all primary hypotheses are accepted. There will be nothing to carry over to the secondary family. It will be quite helpful to give an example. When we started working on multi-stage parallel gatekeeping procedures, we derived the error rate function of the bond-forming procedure. This error rate function is given by alpha times the number of elements in the index set I divided by k, where k is the total number of hypotheses in the primary family. This simply means that the error rate function of the bond-forming test is proportional to the fraction of accepted hypotheses in the primary family. As we said a minute ago, if no hypotheses are accepted, the error rate function is equal to 0. On the other hand, if all hypotheses are accepted, the error rate function is alpha. But what if exactly half of the hypotheses in the primary family are accepted and the other half are rejected? What will be the value of the error rate function for the bond-forming procedure? Based on this simple formula, we see that if half of the hypotheses are accepted, then the error rate function will be alpha over 2. This slide helps us understand the use of error rate functions in parallel gatekeeping procedures. We're going to consider two different extreme outcomes here. The first outcome states that all null hypotheses are rejected in family 1. That immediately implies that the index set of accepted hypotheses, which is A1, is empty. As a result, the error rate function e will be equal to 0, and we can easily show that the local significance level, alpha 2, used in the secondary family, is given by alpha 1 minus the error rate function evaluated of the empty set, which is alpha 1 minus 0, which is equal to alpha. That means that the null hypotheses in the secondary family will be tested at the full alpha level. No alpha will be lost. On the other hand, if there are no null hypotheses that are rejected in family 1, that implies immediately that all of the hypotheses are accepted. So the index set of accepted hypotheses, A1, is equal to N1. That's the index set of all hypotheses in the primary family. The error rate function evaluated at this index set will be given to alpha, and it's quite easy to show, and this is what is represented by this formula, that the local significance level, the amount of alpha that can be transferred over to the secondary family, alpha 2, will be equal to 0. No null hypothesis can be possibly rejected in the secondary family. They will not be even tested. They will be accepted by implication without testing, and that is quite consistent once again with the predefined parallel gatekeeping condition. We cannot reject any of the primary null hypotheses. That tells us immediately that the trial has failed and it's no longer clinically even relevant to consider the secondary families. We're now ready to give a formal definition of a separable multiple testing procedure. A few slides back, I referred to separable procedures as generous procedures, and now I'll explain why I did that. A separable procedure is said to satisfy the separability condition. And this condition states that procedure 1, which is the component procedure used in the primary family, is separable or generous if the error rate function E is strictly less than alpha, provided the index set is a proper subset of the index set N1. It's obviously going to be quite helpful to switch to plain English, and in plain English, using the plain English interpretation of error rate functions, here's what we have. Suppose that we have chosen a separable or generous procedure to test the hypotheses in the primary family. Then a fraction of alpha can be carried over to family 2 if one or more null hypotheses are rejected in that primary family. In other words, with a separable procedure, if we make a single rejection in the primary family, there will still be some alpha available for the secondary hypothesis. This is great news for us because separable procedures, as we can see, provide a foundation for building parallel gatekeeping procedures. But if we consider a non-separable or a greedy procedure in family 1 and only one hypothesis is rejected in this family, then all alpha will be lost. We can no longer build parallel gatekeeping procedures. We now know that to build parallel gatekeeping procedures, we need to focus on separable components in the primary family. The next question we need to answer is, how do we construct separable procedures? To help us answer this very important question, let us examine this table. This table assumes a general problem of testing 3 null hypotheses in the primary family. That's why the index set N1 is equal to 1, 2, 3. And each row in this table shows us the error rate function corresponding to all possible index subsets in the primary family. If the index subset includes the hypothesis 1, 2, and 3, which is the top row, then the error rate function, as we have said multiple times already, is equal to alpha. As we are reducing the number of hypotheses in that index set, for example, if we're down to only 2 hypotheses within the index set, the error rate function is going to be equal to 2 times alpha over 3. With a single hypothesis within that set, the error rate function is reduced to alpha over 3. And of course, if the index set I is empty, the corresponding error rate function is going to be equal to 0. All of this comes directly from the error rate function of the Bonferroni procedure that we defined a few slides back. This was slide 27. And this table shows us immediately that the Bonferroni procedure is a separable or generous procedure because the error rate function is going to be strictly less than alpha if I, that index set I, is a proper subset of the index set N1. However, if we consider the Hagberg procedure and think about the possibility of applying the regular Hagberg procedure in the primary family, we can see immediately that the Hagberg procedure is not separable. That's an example of an efficient or a greedy procedure that tries to use up, consume all of the available alpha. To see why this is happening, let's take a look at the second or third rows in this family. Those would be examples of the cases where the index set is a proper subset of the index set N1. There are only 2 null hypotheses rejected in the primary family, or only 1 null hypothesis is rejected in the primary family. However, the error rate function is still equal to alpha. The separability condition is clearly not satisfied, and this is the reason why we cannot use the regular Hagberg procedure in the primary family. In general, when we talk about the separability condition, I would like to point out that most powerful or stepwise procedures that we discussed in part 1, this includes the Holm, Hagberg, or Hummel procedures, turned out to be non-separable, which is again not a surprise because these are examples of efficient multiple testing procedures that try to utilize all available resources, all available alpha. However, we can force one of those efficient procedures to become separable by applying truncation. A truncated procedure is based on a convex combination between the multiple procedure of interest and the Bonferroni procedure. For example, to construct a truncated version of the Hagberg, we should figure out how to compute a convex combination between the Hagberg and Bonferroni procedures. Of course, it's natural to ask this question at this point. What exactly is a convex combination between multiple testing procedures? We know how to compute convex combinations of 2 points on a two-dimensional plane, but multiple testing procedures are obviously very complicated objects. I'm going to show how to do it over the next several slides, but before we do this, I think it will be helpful to present the following visual analogy. Let's think about the Bonferroni procedure, which is an example of a separable procedure, as a point, the lower point of a segment, and the upper point of that segment or that interval would be the Hagberg procedure, which is non-separable. A truncated version of the Hagberg, which, as I said again, is defined using a convex combination between those two procedures, can be thought of as a point which lies in between those two extremes. Essentially, if we can move just a tiny bit from the Hagberg procedure and get slightly closer to the Bonferroni procedure in this diagram, we're going to end up with a truncated Hagberg, which, as we will show in just a second, will be an example of a separable procedure, and it will help us build powerful gatekeeping procedures that are not Bonferroni based. Let us discuss in a bit more detail the process of defining convex combinations between two multiple testing procedures. The way it is actually done in practice, instead of combining two procedures, we combine the significance levels used by those procedures. Looking at this plot presented on slide 34, what we see here would be the significance levels used for the individual hypothesis. As you remember from part 1, the Hagberg procedure relies on a step-up testing algorithm, which means that it begins testing with the hypothesis that corresponds to the largest p-value. This hypothesis is denoted by h sub 3, and 3 here we use parenthetical notation to differentiate between the original hypothesis h3 and the ordered hypothesis h3. Whenever we look at the corresponding p-value, it will be tested at the full alpha level. We cannot reject that null hypothesis. We will have to consider the next hypothesis in the sequence, and that hypothesis will be tested at the level alpha over 2. Finally, the last hypothesis in the sequence, that's the hypothesis that corresponds to the smallest p-value, will be tested at the level alpha over 3. And this gives us a set of two linear segments that we see on the slide. On the other hand, as another extreme, we can consider the set of significance levels used by the Bonferroni procedure. In this case, it is represented by a dotted line, because with the Bonferroni procedure, as you remember, each p-value is tested at the same significance level, and that significance level is given by alpha over 3. That's the reason this line is flat in this figure. The significance levels are constant across the hypothesis. Now, if we can construct any step-up testing procedure which utilizes the significance levels that lie in between those two extremes, between the solid segments and the dotted line at the bottom here, for example, we can consider a procedure which utilizes the significance levels given by this dashed curve. This would be an example of a truncated procedure. More formally, when we talk about a truncated version of the Hagberg procedure, what we do here is to be able to find adjusted significance levels for the individual null hypothesis in the data-driven sequence. We take the significance levels utilized by the Bonferroni procedure, and those are shown on the left-hand side of this table. All of those significance levels are simply alpha over 3. Now, moving on to the right-hand part of this table, we see the adjusted significance levels used by the Hagberg procedure. Those are given by alpha over 3. That's the significance level for the smallest p-value. Then alpha over 2 for the second smallest p-value. And finally, alpha over 1, or simply alpha. That's the adjusted significance level for the largest p-value. And to be able to compute the adjusted significance levels for a truncated Hogberg procedure, we simply take a convex combination of those two columns. That is what we see in the central column in this table. The convexity parameter in this convex combination is known as the truncation parameter. It is denoted by gamma. We can think about it also as a greediness parameter. This parameter ranges from 0 to 1. The decision rules that are used by a truncated Hogberg procedure are defined on the slide. They are conceptually quite similar to the decision rules employed by the regular Hogberg procedure. The only difference here is that instead of using the full alpha level, for example, for the largest p-value in this multiplicity problem, we'll look, as I explained on slide 36, we'll look at a convex combination between the full level alpha and the significance level, which is alpha over 3, that would have been used by the bond-forming procedure. The same principle applies to the significance level that would be applied to the second largest p-value, and finally the significance level that will be applied to the smallest p-value. This significance level is shown at the bottom of the slide. The most important properties of any truncated Hogberg procedure are presented on this slide. It is very helpful to consider the following special cases. It is very important to remember that if gamma, which is the truncation parameter, is set to 0, we end up with a generous or separable procedure, because in this case, a truncated Hogberg procedure simplifies to the basic bond-forming procedure. This will be one extreme. The other extreme is achieved when the truncation parameter is set to 1. In this case, the truncated Hogberg procedure simplifies to the regular Hogberg, and we end up with a greedy or non-separable procedure. To be able to construct parallel gatekeeping procedures, we need to find a subset of generous or separable procedure, and as shown at the bottom of the slide, the separability condition is met for a truncated Hogberg procedure. It will be separable, and it can be used in parallel gatekeeping procedures if gamma is strictly less than 1. Gamma could be potentially as low as 0, but this would not be consistent with our objective of building an efficient parallel gatekeeping procedure. Our goal, as we'll explain later in this module, would be choose a value of gamma that is reasonably close to 1 to help maximize power in the primary family, but at the same time we cannot set the truncation parameter to 1, because that is going to give us a separable procedure and is going to violate the parallel gatekeeping restriction in the primary family. We are getting fairly close to the end of Module C, and we have covered a lot of high-level methodological material, so the time has come for us to begin looking at numerical examples to get a better feel for the gatekeeping procedures that we have introduced in this module, and we'll also discuss issues related to software implementation of those procedures. We're going to do a quick numeric example to illustrate and compare the performance of the nonparametric and semiparametric gatekeeping procedures that we have introduced so far, using example 2 based on the type 2 diabetes trial. The table on this slide defines the raw one-sided p-values for the hypotheses that will be tested in this clinical trial, and we're going to discuss the steps that we'll need to take to implement the gatekeeping procedures, with the ultimate goal of controlling the global family-wise error rate in this multiplicity problem at a one-sided alpha of 0.025. The parallel gatekeeping procedures that will be compared as part of this numeric example are defined on this slide, beginning with the nonparametric parallel gatekeeping procedure. As we have discussed before, we're going to apply the basic Bonferroni procedure within the primary family, and it will be followed by a univariate test in the secondary family, because that family, of course, includes a single null hypothesis. The only difference between this approach and the semiparametric parallel gatekeeping procedure is that this second procedure employs the truncated Hogberg procedure with the gamma set to 0.7, the truncation parameter gamma set to 0.7 in the primary family, and within the secondary family, since there is really no multiplicity that needs to be accounted for, once again we're going to apply a univariate test. I am going to use a series of graphical summaries that I think are quite helpful because they facilitate the general understanding of the underlying decision rules that are employed by the nonparametric and the semiparametric gatekeeping procedures. With the nonparametric procedure, as we said just a minute ago, we're going to begin by testing the null hypothesis in the primary family by applying the basic Bonferroni procedure. As shown on this diagram, we're now focusing on the two hypotheses H1 and H2 in family 1, and we have two parameters. First of all, we have the alpha 1 parameter, that is the local alpha level that will be used within this family. That is the incoming parameter, if you will, and there's an outgoing parameter shown at the bottom of the box, that is alpha 2. That is the local level that will be applied in the secondary family. Now, within this primary family, we see that the p-values for the two hypotheses are given by 0.0082 and 0.0174, and therefore it is quite easy to verify that with the basic Bonferroni test using a simple alpha splitting strategy, the significance level that will be used to test the individual null hypothesis is equal to 0.0125. It is shown at the bottom of the slide, and at this significance level, only one of those two hypotheses, specifically H1, will be rejected. H2 is grayed out because this hypothesis failed to be rejected by the Bonferroni procedure. Given that this family serves as a parallel gatekeeper for the secondary family, we make a decision, and this is good news for us, is that the primary objective of this trial has been met. We are ready to continue to test the secondary hypothesis. Unfortunately, there is a certain price that we'll need to pay for failing to reject the hypothesis H2 that will be reflected in a reduced alpha level that will be carried over to family 2. Only half of the original alpha, specifically 0.0125, will be carried over to the secondary family. The decision rule applied within the secondary family is quite straightforward, of course, because it's based on a simple univariate test. Since only half of the alpha is available to us at this stage of the testing algorithm, this local significance level will be applied to the only hypothesis in the secondary family. The p-value corresponding to that hypothesis is 0.0202. This p-value is not significant at the alpha level given by alpha 2, and as a result, we conclude that the secondary hypothesis H3 cannot be rejected. It will be accepted by the nonparametric gatekeeping procedure. It will be quite interesting now to apply the semiparametric gatekeeping procedure to the same set of p-values. And to be able to do this, we'll need to first of all set the stage, and I'm going to explain the decision rules that will be first of all utilized in the primary family. Then we'll need to discuss the alpha propagation rules. We'll need to determine how much alpha can be carried over to the secondary family, depending on the outcomes observed in the primary family. And that will be discussed on the next several slides. But on this slide, slide 44, I simply define the decision rules used by the truncated Hogberg procedure with the truncation parameter set to gamma in the primary family. These decision rules are based on ordered p-values because, as we discussed in part 1, the Hogberg procedure is a stepwise procedure. In fact, this is an example of a step-up multiple testing procedure. To be able to apply it, we'll need to define the ordered p-value first, and they're defined using the standard parenthetical notation. We differentiate between the smaller and the larger p-value. Now, being a stepwise procedure, the Hogberg procedure will reject both hypotheses in the primary family if the larger of the two p-values is less than or equal to alpha plus gamma times alpha over 2. If the larger p-value is not below this threshold, then the Hogberg procedure is going to step down to the smaller p-value, and the corresponding hypothesis will be rejected if that smaller p-value is less than or equal to alpha over 2. To determine the local alpha level to be used in the secondary family, it is denoted by alpha 2. We will need to, first of all, compute the error rate function of the truncated procedure. The error rate function is shown on this slide, and this error rate function, as we have said many times before, plays a key role, a central role in defining the alpha propagation rule for the secondary family. This alpha propagation rule is defined on this slide. Here we're going to take a close look at 3 different possible outcomes in family 1. We're going to begin with the scenario where no null hypotheses are rejected in family 1, and then we're going to apply the error rate function of the truncated Hogberg procedure to see how much alpha can be then carried over to the secondary family. In this case, since there are no rejections in family 1, the set of accepted hypotheses, denoted by A1, includes the indices 1 and 2. It's quite easy to show using the formula defined on slide 45 that the error rate function evaluated for this set of accepted hypotheses is actually equal to alpha. And as a result, the local level, the local significance level in the secondary family, alpha 2, is equal to alpha minus alpha, and that obviously ends up being 0. That's a very important and actually fairly intuitive conclusion, and that is consistent with the concept of a parallel gatekeeper. Since we failed to reject any hypothesis in the primary family, we essentially failed to pass the gatekeeper, and whatever families are included in the secondary family, will be automatically accepted. And numerically, that is reflected by the fact that no alpha can be transferred to the secondary family. The news will be slightly better when we look at the second and the third outcome, and that is because in the second outcome or in the third outcome, some rejections are made in the primary family. For example, under the second scenario, we assume that exactly one null hypothesis is rejected in the primary family, in which case the set of accepted hypotheses A1 is either equal to 1 or 2. It depends on which hypothesis is rejected. Since we assume that the primary hypotheses are equally weighted, it doesn't really matter. We can put both of those outcomes in the same bucket under the same scenario. And by applying the formula for the error rate function of the truncated Hogberg procedure, that again comes from slide 45, it is quite easy to verify that the significance level in the secondary family, alpha 2, is equal to 1 minus gamma times alpha over 2. A very important condition that we applied before was the condition of separability. We said that parallel gatekeeping procedures can be constructed only if a separable, for example, a truncated procedure is applied in the primary family, and that is characterized by the fact that gamma must be less than 1. Now you can see clearly why it is so important to consider separable procedures in the primary family. If gamma is indeed set to 1, then the significance level in the secondary family will end up being 0, which is not consistent with the conditions around the parallel gatekeeping restriction. Finally, the most optimistic for us case here is the last case when both hypotheses are rejected in the primary family. In this case, the set of accepted hypotheses A1 is empty. The error rate function in this case is equal to 0, and therefore subtracting 0 from alpha, we conclude that the significance level in the secondary family, alpha 2, is simply equal to alpha. This is great news for us because in this case, once we've been able to reject both null hypotheses in the primary family, we can now transfer the entire alpha level to the secondary family. That is obviously going to improve the probability of success in the secondary family. Using this information, we can now go ahead and set up the decision rules for the Hagberg-based parallel gatekeeping procedure in example 2. We're going to begin with the rejection rules that will be applied in the primary family. This is the diagram that you see on this slide. And as before, when we discussed similar rejection rules for the nonparametric gatekeeping procedure, we're going to pay close attention to the local alpha level, which is equal to alpha 1 or 0.025 that will be applied within the primary family. We're also going to pay close attention to how much alpha will be transferred to the secondary family. This quantity is denoted by alpha 2. That's the quantity that is shown below the primary family. It is quite easy to show using the rules that we have discussed for the truncated Hagberg procedure that the larger of those two p-values in the primary family is in fact less than or equal to 1 plus gamma times alpha over 2. And as a result, we can claim that both hypotheses are rejected in the primary family. With this information, we can state that the primary objective of the trial has been met. We can now proceed to the secondary family, and we can also compute how much alpha can be carried over to that secondary family. Since there were no accepted hypotheses within the primary family, all of the alpha will be transferred to family 2. This full alpha level of 0.025 will now be applied to the only hypothesis in the secondary family, to the hypothesis H3, and it's quite easy to see that the p-value corresponding to this hypothesis, which is 0.0202, is significant at this level, and therefore the Hagberg-based gatekeeping procedure is going to reject not only all of the hypotheses in the primary family, but also the only hypothesis in the secondary family. We can now go over the general conclusions that facilitate a comparison of gatekeeping procedures in this particular clinical trial example. They're in fact representative of more general settings. It is quite common for non-parametric parallel gatekeeping procedures to reject fewer hypotheses than corresponding semiparametric parallel gatekeeping procedures. In this particular case, we see that a single null hypothesis was rejected by the Bonferroni-based procedure, and with the Hagberg-based procedure, all three null hypotheses were rejected. This is due to a number of factors. First of all, within the semiparametric testing approach, a more powerful component procedure is applied in family 1. It's the truncated Hogberg, which is uniformly more powerful than the basic bond-forming procedure. And secondly, in more general settings, when there are multiple hypotheses included in the secondary family, we can also claim higher power in that secondary family, potentially in other families, simply because a more powerful component would be used in those families when the semiparametric testing approach is considered. An important point I would like to make here is related to the selection of a reasonable value for the truncation parameter gamma, which would be used in the primary family. There are several publications that have discussed the problem of identifying an optimal value of the truncation parameter, and the general conclusion is that this optimal value would be driven by the effect sizes in families 1 and 2, and it would also depend on the correlation, the between family correlation coefficient or coefficients. My general recommendation here would be to consider a set of meaningful clinical trial optimization methods. Once again, there are some publications, real clinical trials that have benefited from application of clinical trial optimization methods that are aimed at identifying optimal multiplicity adjustments in the context of semiparametric parallel gatekeeping procedures. Those problems simplify to a fairly straightforward problems of selecting an optimal value of the truncation parameter. And here I would like to mention very quickly a book that we published in 2017. The title of the book is Clinical Trial Optimization Using R. This book utilizes the powerful Mediana package to consider clinical trial optimization problems in multiple settings, but the second chapter in this book deals with an important problem of optimally selecting analysis strategies, including multiplicity adjustments in phase 3 trials with multiple objectives. There is one section left in this module. We still need to discuss the important topic of software implementation of parallel gatekeeping procedures. And on this slide, I will summarize the key points from this module. In this module, we have restricted our attention to a class of multiplicity problems with several families of null hypotheses, where each family serves as a parallel gatekeeper for the next family. We have considered two classes of parallel gatekeeping procedures that are defined using nonparametric tests, for example, the Bonferroni or Holm tests, and also procedures based on semiparametric tests, such as Hogberg-based parallel gatekeeping procedures. The nonparametric approach to building gatekeeping procedures is generally inefficient because the resulting procedures are based on a basic alpha splitting approach and do not account for the available distributional information. For example, for positive correlations among hypothesis test statistics in a multiplicity problem. With a semiparametric approach, or more generally with a parametric approach, a trial sponsor can build parallel gatekeeping procedures that take the available distributional information into account, which results in higher power for each individual null hypothesis. Both approaches to defining parallel gatekeeping procedures rely on straightforward testing algorithms that are easy to implement, and the decision rules are easy to communicate to non-statisticians. We're going to discuss software implementation options for parallel gatekeeping procedures, both in SAS and in R. And beginning with SAS, semiparametric parallel gatekeeping procedures can be implemented using the mixed gate macro, which is a custom macro that was developed by Thomas Brechenmacher. And for more information and numerous examples, I would like to encourage you to read a book chapter in a recent book published by SAS Press. The title of the book is Analysis of Clinical Trials Using SAS. Thomas has written this macro to support a fairly broad class of gatekeeping procedures that includes parallel gatekeeping procedures, but we're going to come back to this custom macro in Module D. In this section, I'm going to show how this macro can be used to perform multiplicity adjustments using the Hogberg-based parallel gatekeeping procedure that we introduced earlier in this module in example 2, based on the type 2 diabetes trial. With this gatekeeping procedure, we're going to apply the truncated Hogberg procedure with the truncation parameter set to 0.7 in the primary family or in family 1, and in family 2, as we have said, there's only one hypothesis left, and therefore there are no additional sources of multiplicity. It will be sufficient to carry out a standard univariate test. The p-values that will be used in this example match the p-values that we used earlier in this module. The p-values in the primary family are given by 0.0082 and 0.0174, and in the secondary family the p-value is 0.0202. Slide 55 shows the SAS code that needs to be run to perform a multiplicity adjustment based on this parallel gatekeeping procedure. This SAS code consists of 3 separate modules. The first module includes the specification of a data set called EX2, which stands for example 2, and this data set defines most of the important aspects of this multiplicity problem. This includes the specification of the hypothesis to be tested. They correspond to the rows in this data set. There are 3 rows, 1 hypothesis per row, and within each row we specify 5 variables. The first variable defines the hypothesis label. The second variable, family, defines the family index. You can see here that the family index is equal to 1 for the first 2 rows, which means that the first 2 hypotheses are included in the first family and the last hypothesis is included in the second family. And secondly, we have a set of binary indicators that are included in the parallel and serial variables. Those binary indicators are used to define parallel or serial gatekeeping restrictions. In this case, we're dealing with a multiplicity problem with a parallel gatekeeper, and as a result, when it comes to the last row in this data set, we need to specify the conditions under which this hypothesis H3 will be tested. If you take a closer look at the parallel variable, you will notice that the first 2 indicators, or the first 2 digits in this variable, are set to 1. So the variable is equal to 1, 1, 0 for the last hypothesis in this multiplicity problem, which means that the first 2 families are included in the parallel gatekeeping set for the last hypothesis. It is sufficient for any one of those first 2 hypotheses to be rejected before we can proceed to testing the hypothesis H3. When it comes to the serial variable, all of the indicators are set to 0, and that reflects the fact that there are no serial gatekeeping restrictions in this multiplicity problem. And the last variable included in this data set is the one-sided p-value for each individual null hypothesis, and they're equal to, as you can see, to 0.08082, 0.0174, and 0.0202. The next step here is the invocation of the mixed gate macro, This macro is called by supplying the following 5 arguments. The first argument is the data set that once again defines the key aspects of this multiplicity problem. We are going to pass the ex2 dataset to the macro. Secondly, we're going to specify the mixture method. We will talk more about mixture methods for defining flexible gatekeeping strategies in the next module. For now, we're going to assume that the standard method is what is commonly used for defining gatekeeping procedures. The third argument for the mixed gate macro is the test argument. It specifies the component procedures that will be applied to each individual family in this multiplicity problem. In this particular case, there are 2 different families, and we can see here that the Hogberg procedure will be applied to the first family with the truncation parameter equal to gamma of 0.7. The truncation parameter for the second family is not explicitly defined because it is set to 1 by default, and therefore to specify this Hogberg-based parallel gatekeeping procedure, it is sufficient to set the test argument to Hogberg and the gamma argument to 0.7. The last argument of this macro is the name of the data set where the multiplicity adjusted p-values will be saved. It's ADJP, which stands for the adjusted p-value. And the last 3 lines of this short SAS program are simply used to print out the multiplicity adjusted p-values. The multiplicity adjusted p-values generated by the mixed gate macro are shown on this slide. They correspond to the 3 hypotheses in this problem. The first p-value corresponds to the hypothesis H1, and then H2, and then H3. We can see here that when we apply a one-sided alpha level of 0.025, it is immediately clear that all 3 multiplicity adjusted p-values are significant, which indicates that the Hogberg-based parallel gatekeeping procedure rejected all 3 hypotheses in this multiplicity problem, which is consistent with the numerical example that we went over a few minutes ago. Moving on to the discussion of software implementation options for gatekeeping procedures in R, I would like to mention the Mediana package that I referred to multiple times in part 1 of this online training course. This is an R package that was developed a few years ago to support a broad set of clinical trial simulation options. It also includes a number of functions that support popular multiplicity adjustments. For example, the adjust p-values function supports multiplicity adjustments based on commonly used multiple testing procedures, and there's also the adjust CIs function that computes multiplicity adjusted or simultaneous confidence intervals. In the context of this module, we're mostly interested about ways of performing multiplicity adjustments based on parallel gatekeeping procedures, and this function supports both nonparametric and semiparametric gatekeeping procedures. I would like to encourage you to learn more about other options available within this R package. You can see the websites, a general website that provides information about the package and also a reference to the CRAN website from which the package can be downloaded. And I'd like to mention that my longtime collaborator Gautier Paul has also created a very nice online manual that provides information about the Mediana package. Obviously, it emphasizes the simulation-based approaches that are supported by this package, but it also provides information about multiplicity adjustment options. To carry out a multiplicity adjustment based on the semiparametric or Hogberg-based parallel gatekeeping procedure that we introduced earlier in this module, we can run the following R code that relies on the adjust p-values function. I'm going to go through this code carefully, looking at each line at a time. The first line in this program specifies a vector of the raw or unadjusted or marginal p-values for the hypothesis of interest in example 2. Secondly, when it comes to the families variable, this is the variable that defines the assignment of the individual hypotheses to the two families. We can see here that family 1 is defined by including the hypotheses with the indices 1 and 2, and family 2 includes a single hypothesis with the index 3, which means the hypothesis H3. Moving on to the component procedures object, this is the object that defines the family-specific component procedures. In this case, as we've said before, we're going to use the Hogberg procedure, a truncated version of the Hogberg procedure, I should say, in the primary family. In the secondary family, we're going to use a univariate test, which is a special case of any multiple testing procedure, including the Hogberg procedure. The next object or the next list is the gamma variable. It specifies the family-specific truncation parameters. In this case, the truncation parameter for the Hogberg procedure to be used in the primary family is 0.7, and within the second family, we're going to use the regular Hogberg procedure, which, given that there's only one hypothesis in this family, is going to simplify to univariate test. All of those variables that define the structure of the multiplicity problem and the proposed gatekeeping procedure are going to be passed to the adjust p-values function. This adjust p-values function is going to compute multiplicity adjusted p-values. They will be saved to the ADJP variable, and the very last line on this slide is going to print out the adjusted p-values. This is the last slide in Module C, and it simply displays the multiplicity adjusted p-values produced by the adjust p-values function. They are identical to the adjusted p-values produced by the mixed gate macro, and they also indicate that in this particular clinical trial example, the Hogberg parallel gatekeeping procedure rejected all null hypotheses.